You know that feeling, right? You're driving, windows down, music up, and the road beneath you is just perfect. Smooth, quiet, almost effortless.
Yeah, absolutely.
But have you ever stopped to really think about what goes into creating that seemingly simple, durable ribbon of asphalt? It's far more intricate than just pouring some hot black stuff.
It truly is.
Yeah.
What seems like a straightforward surface is actually the culmination of incredibly precise engineering, um, advanced chemistry, and really synchronized teamwork. It's a whole hidden world beneath your tires.
And that's exactly what we're diving into today. We're taking a deep dive into the fascinating, often invisible world of asphalt pavement construction.
Hmm.
Our main source for this journey is Construction of Quality Asphalt Pavements, MS-22, a pretty comprehensive manual from the Asphalt Institute. It's been guiding experts in this field for, 35 years now?
That's right. It's a cornerstone resource.
So our mission today is to kind of extract the essential technical information and best practices, giving you a shortcut to understanding what truly makes a road built to last.
We'll guide you from the fundamental raw materials and the intricate mix design all the way through the intense choreography of plant production, the critical steps of placement and compaction, and finally, the rigorous quality control that ensures longevity.
Because, as the manual clearly states, a successful pavement needs that synchronized process, right?
Exactly. It says a breakdown in any single part typically comes to a halt and quality suffers.
Yeah.
Everything has to work together.
So let's start at the very beginning with what sounds like a fundamental truth for any kind of construction, really.
Okay.
The manual presents it as a core principle. A pavement is only as good as the materials and workmanship that go into it.
Hmm.
No amount of sophisticated equipment can make up for use of poor materials or poor construction practices. That really sets the stage for the level of precision we're talking about, doesn't it?
It absolutely does. It underscores that every single component and every single step is vital. Take the asphalt binder, for instance. People often think of it as just the glue, but its behavior is surprisingly complex, and it's key to the road's performance.
How so? I mean, I just picture it as, well, binding everything together.
Well, it does, but how it binds changes. In hot conditions, like a scorching desert or even under slow, heavy traffic, it acts more like a viscous liquid.
Ah, okay. Like thick honey or something.
Sort of, yeah.
Yeah.
And that can lead to what's called plastic deformation. That's what you see as ruts or grooves forming in the road surface.
Right, I've definitely seen those. So if it gets soft and liquid-like when it's hot, how do engineers stop those ruts forming? What's the fix?
That's a great question. The solution is actually pretty straightforward in concept. You specify stiffer asphalt binders for hot climates.
Stiffer binders, got it.
It sounds like a small detail in the overall recipe, but it has a huge impact on preventing that unwanted deformation and extending the road's life.
And what about cold weather? Does it change then too?
It does the opposite. In cold conditions or under the rapid loading from fast traffic, that same asphalt binder behaves more like an elastic solid.
Elastic, so it bounces back.
Exactly. It deforms under the stress of a tire,
Yeah.
but then it recovers its original shape. And that's crucial for preventing cracking, especially in colder weather or under heavy, fast loads.
Okay, so you have this binder, this almost chameleon-like material adapting to heat and speed, but then there are the aggregates. I'm guessing they're a bit more involved than just rocks, right?
Oh, much more. We're talking about very specific types and sizes. You've got the larger gravel, then sand, and then these ultrafine materials called mineral filler or dust. Some of these particles are tiny, smaller than a human hair.
Wow.
And here's something that might seem counterintuitive. Those finer materials, they actually increase the liquid asphalt demand of a mixture.
Wait, hang on. Finer stuff needs more binder. I think it would fill the gaps and need less. What's going on there?
Right. It seems backwards. But think about surface area. Those tiny particles, even though they're small individually, create a massive total surface area that the binder needs to cope.
Ah, okay. More surface area, more paint needed, basically.
Exactly. But then it gets even more interesting. The ultrafine mineral filler, we're talking particles smaller than red blood cells here, they can actually act as a binder extender.
Extender, so it helps the binder go further.
Yeah, and it can also stiffen the mix. It's this really delicate balancing act that mix designers work hard to perfect. Getting just the right amount of fines is critical.
So it's all about controlling that balance. And to get it right, I imagine they must do a ton of testing on these aggregates.
Absolutely. A fundamental test is sieve analysis. That tells us the gradation, the distribution of all the different particle sizes.
Okay.
And then there's another really crucial one called the sand equivalent test.
Sand equivalent, what's that? checking for?
It basically tells us if the really fine stuff mixed in with the sand is actual, good inert sand, or if it's potentially troublesome plastic fines.
Plastic fines, like
But
clay.
exactly, tiny clay particles. Those can interfere with how well the binder sticks to the aggregate, and that can lead to moisture damage and premature failure down the road. So this test helps ensure we have the right kind of fines for strength and durability.
That level of detail, it really does sound like a chef perfecting a recipe. Is it that much like a culinary art balancing
It
everything?
genuinely is. The mixed design is exactly that. The detailed recipe. It balances strength, durability, workability, everything.
So it lists out all the ingredients.
Precisely. It specifies the exact blend percentages of binder, different aggregates, any additives, along with lots of test data. And it all culminates in what's called the job mix formula, or JMF.
The JMF, okay.
And that JMF includes specific target values and, crucially, very tight tolerances for things like the binder content. For example, the binder might need to be within, say, plus or minus 0.3% of the target. Very precise.
That is incredibly tight. But I guess the real world isn't always as neat as the lab. What happens if they need to adjust the mix out on the job site? Can they do that without messing up the quality?
That's a constant challenge. Natural variations in the aggregates, even from the same quarry, mean that small field adjustments are often needed. It's expected.
So how do they manage it?
It's about continuous monitoring and understanding that variability. The goal is always to keep the produced mix within the specified JMF tolerances. This
Hmm.
ensures they hit the critical volumetric properties, especially the air voids in the final pavement.
Near voids, okay.
Yeah, if the mix starts deviating, maybe the air voids are trending too high or too low, they have to investigate immediately. Is it a sampling issue? Is the aggregate gradation changing? Is something off in the plant production? For instance, if the air voids are consistently too low, it might indicate a problem called collapse of VMA.
Collapse of VMA. What does VMA stand for, and why is it bad if it collapses?
Good question. VMA is voids in mineral aggregate. Think of it as the space between the aggregate particles before you add the binder. It's like the little network of gaps.
Okay, the empty space.
Right. And that space is crucial. It needs to be large enough to hold the required amount of asphalt binder, plus leave enough room for the necessary air voids in the final compacted pavement. If that VMA structure collapses, meaning the aggregates packed together too tightly, leaving too little space, you literally don't have enough room for the binder to properly coat everything and maintain those air voids.
So what happens then? The mix is too dense.
It might seem dense, but it's actually a bad thing. The mix becomes starved for binder, it can be brittle, lacks flexibility, and it won't have the durability needed. It often leads to premature cracking. So maintaining sufficient VMA is critical.
Wow, okay, so the invisible spaces are just as important as the rocks themselves. Fascinating. Now, another thing mentioned is using reclaimed asphalt pavement, or RAP. That sounds like a great idea. Very sustainable.
It definitely has big benefits. Economically, it reduces the need for expensive virgin binder and aggregates. And environmentally, it's obviously great to reuse existing resources.
But are there downsides? Or things to watch out for?
Oh, absolutely. It's critically important to know the source, stockpiling, and variability of RAP. You can't just treat all RAP the same.
Why not? Isn't old asphalt just old asphalt?
Not really. Think about it. RAP from an old city street that's seen lots of stop-and-go traffic and maybe different maintenance over the years, that could be substantially different from RAP taken from a high-speed highway. The original mix design, the aging of the binder, it all varies.
Ah, okay. So you need to understand its history.
Exactly. That variability directly impacts the new mix design and the quality control needed. You have to account for the properties of the RAP binder and aggregates when you create the new recipe.
Makes sense. And speaking of performance, let's circle back to those air voids. Why are they so fundamentally important for how the road performs over time?
All right, this is where it gets really interesting from an engineering perspective. Air voids in asphalt content have a significant effect on a mixture's fatigue resistance.
Fatigue resistance. That's how well it holds up to traffic.
Exactly. It's the pavement's ability to withstand repeated wheel loads, millions of them, without cracking or falling apart.
Yeah.
And what the research clearly shows is that as the percentage of air voids increases, the fatigue resistance is drastically reduced.
So too much air is definitely bad, like holes weakening the structure.
Precisely. Think of those tiny air pockets as points of weakness. Under repeated stress, cracks initiate and grow from those voids, kind of like bending a paperclip back and forth until it snaps.
Okay. And does anything else affect that fatigue resistance?
Yes, definitely. Old aged binder or using too much RAP or another recycled material called RAS, recycled asphalt shingles, can also reduce fatigue life because the binder is already stiffer and more brittle.
But can you improve it?
You can. Using a polymer-modified asphalt binder can significantly improve fatigue resistance. Those polymers make the binder much more flexible and tougher, allowing it to withstand more bending cycles before cracking.
Polymer modified.
Okay.
Okay. So how do they actually measure these critical air voids?
They use two key density measurements. First is the theoretical maximum specific gravity, usually called GEO. That's the density of the loose mix with absolutely zero air voids like a solid block of the material.
The theoretical maximum. Got it.
Then there's the bulk specific gravity,
Right.
or FM. That's the density of the actual compacted sample, including the air voids within it.
I need the real world density.
Right. And since the GRM represents the mix with no air, it will always be a larger number than the GRM, unless you somehow achieved a theoretical 0% air voids in your sample, which is practically impossible.
So you compare the two.
Exactly. By comparing the GUM to the GM, you can calculate the precise percentage of air voids, usually denoted as PA, in the compacted pavement.
And is that straightforward to measure?
Usually, but sometimes compacted samples can absorb water during the GMN test, which messes up the measurement. In those cases, they often use a specialized method called the Corloki procedure.
Corloke.
Yeah, it involves vacuum sealing the sample in a plastic bag before weighing it underwater. It prevents water absorption and gives a much more accurate jam, especially for coarser or more porous mixes.
Clever. Are there other key performance tests?
Oh yes. A very common one is the Hamburg wheel tracking test. They run a loaded wheel back and forth over a sample, often underwater, to see how quickly it ruts. It measures both rutting susceptibility and moisture susceptibility. How well the mix resists stripping, where the binder peels off the aggregate due to water. Very important for predicting real-world performance.
Okay, so they've got the perfect recipe, the materials are tested and ready. Now comes the big production part, getting it from the plant onto the road. The manual talks about a balanced paving operation. What does that mean in practice?
It's all about synchronization. You need the hauling, placement, or laydown and compaction phases to work together seamlessly. Think of it like a finely tuned assembly line, but one that's moving down the road.
So trucks arriving just in time, the paver moving steadily?
Exactly. If the trucks delivering the mix arrive too slowly, the paver has to stop, creating bumps and cold joints. If they arrive too fast, they bunch up. If the rollers can't keep up with the paver,
The mix cools down too much before it's compacted.
precisely. If any of those phases aren't synchronized and in balance, achieving that continuous high-quality pavement becomes incredibly difficult. Quality suffers.
So let's peek inside the asphalt plant itself for a minute. How do they handle the raw materials there before they even get mixed?
Well, the liquid asphalt binder that's stored in big insulated and heated tanks, and maintaining the right temperature is critical. Sufficient binder temperature is maintained throughout the process.
Why is temperature so vital for the binder?
It directly affects its viscosity or thickness. Too cold, and won't coat the aggregate particles properly. Too hot, and you can damage the binder or waste energy. So temperature control is key for its coating characteristics.
Okay. And what about the aggregates? The rocks and sand?
Managing aggregates is a big challenge, mainly because of segregation.
Segregation, meaning the big rocks separate from the small ones.
Exactly. When you build stockpiles, the larger particles tend to roll to the outside and bottom, leaving the finer stuff concentrated in the middle. If you don't manage that carefully when feeding the plant, your mix consistency goes out the window.
So how do they prevent that?
They use things like bulkheads or dividers between different aggregate stockpiles. They also use specific loading techniques with front-end loaders to minimize segregation when picking up material. Handling larger, multi-sized aggregates properly is much more complex than managing fine, uniform sand.
Right. And once they've got the aggregates managed, they go into the dryer.
Yep, into the dryer drum. This huge rotating drum does two things. It dries off any moisture, and it heats the aggregates up to the precise temperature needed for mixing. They use pyrometers, like infrared thermometers, to constantly monitor and control that aggregate temperature leaving the drum.
And then the mixing happens. Are all plants the same?
No, there are basically two main types. You have batch plants, which, as the name suggests, produce the mix one batch at a time. They weigh out the aggregate and binder for each batch, mix it in a separate mixer called a pug mill, and then discharge it.
Okay, like making cookies one tray at a time.
Pretty much. And then you have drum mix plants, which are continuous. Aggregate and binder are continuously fed into a long, rotating drum where they're mixed together as they travel along its length.
More like an assembly line. Is one better than the other?
They both have their places. Batch plants offer maybe a bit more precision for specialized mixes or smaller quantities. Drum plants are generally higher production, great for large highway jobs.
And I read something about batch plants having a limit on recycled asphalt.
That's right. Because of how they heat and mix, batch plants typically have a practical limit of around 25% for RDP content. It's harder for them to efficiently transfer heat to the RAP without overheating the virgin aggregate or producing emissions. Drum plants can usually handle higher RAP percentages more easily because the mixing and heating happen together.
Speaking of emissions, I imagine drying and heating all that rock creates a lot of dust.
It definitely does. Dust collection is a major part of any asphalt plant, essential for meeting air quality regulations. The most common system is a baghouse.
Like a giant vacuum cleaner.
Essentially, yes. It filters the exhaust air through hundreds of fabric bags, and they can be over 99% efficient at capturing those fine dust particles, the -200 material. Some smaller or older plants might use wet scrubbers, which use water sprays to capture the dust.
Okay, so the mix is made, quality controlled at the plant. Now it needs to get to the paving site. What's new in hauling?
Well, you have your standard end dump trucks, which are very common, and bottom dump trucks, which are often used for windrow paving. They lay the asphalt in a continuous pile or windrow on the grade, and then a machine picks it up and feeds the paver.
Right.
But a really important innovation is the horizontal discharge, or live bottom truck. Instead of raising the bed to dump, it uses a conveyor belt system at the bottom of the truck bed to discharge the mix.
Ah, so it pushes it out horizontally. What's the advantage there?
Several big ones. Safety is huge. No risk of the raised bed hitting overhead lines or tipping on uneven ground. Plus, it significantly minimizes segregation because the mix moves out as a mass rather than tumbling out. It also gives a more controlled flow into the paver or transfer device.
I can see how that would help keep the mix uniform, and temperature during transport must be critical too, right?
Absolutely vital. If that hot mix cools down too much on the way to the site, it can start to stick to the sides of trucks and form clumps.
And those clumps cause problems.
Big problems. Those cool lumps don't blend in properly, and they can cause streaking and tearing of the mat as it goes through the paver screed. You lose that smooth, uniform finish. So trucks are often insulated, and tarping is essential, especially in cooler weather.
And once the truck gets to the paver, there's someone actually coordinating the dumping.
Yes, and that person, the dump person, plays a crucial, often overlooked role. They direct the truck backing up, control the rate of unloading into the paver hopper, and they have a major influence on both the smoothness of the mat and the potential for segregation. A good dump person keeps the flow smooth and consistent.
An unsung hero of the paving crew.
Definitely. And for larger, high-production jobs, you'll often see another piece of equipment linking the trucks and the paver. The Materials Transfer Vehicle, or MTV.
Right, the MTV, what exactly does that do?
It's a heavy piece of equipment that essentially acts as a mobile surge, silo, and remixer. The trucks dump into the MTV, not directly into the paver.
And why is that better?
A few key reasons. First, it uncouples the truck from the paver. The paver can keep moving continuously while trucks exchange at the MTV, eliminating stops and starts, which are a major cause of bumps.
Ah, keeps the paver moving.
Second, it offers on-site blending of the mixture. As the mix goes through the MTV, it gets remixed, which helps eliminate temperature differences, thermal segregation, and material segregation that might have happened in the truck. This provides a much more uniform mix temperature and consistency to the paver.
So, better quality control right before laydown.
Exactly. And third, it can sometimes even reduce the number of trucks needed because they can discharge faster into the MTV and get back to plant quicker. It's a vital piece for high-spec paving jobs.
Okay, so the mix is finally at the paver, uniform, right temperature. Now it's time to actually lay it down right. What needs to happen before the paver starts moving?
Preparation of the surface underneath is critical. You can't just pave over anything. The condition of that underlying layer is paramount.
Makes sense. Garbage in, garbage out.
Pretty much. And ensuring good layer bonding is absolutely essential. That's where the tack coat comes in.
The sticky stuff.
Yeah, it's basically a thin layer of liquid asphalt sprayed onto the existing surface. It needs to be applied uniformly to all horizontal and even vertical surfaces, like the edge of a previous lane or a curb. It acts like glue, ensuring the new asphalt layer sticks firmly to the layer below. Without a good tack coat, layers can slip and the pavement structure is compromised.
Okay, tack coat is essential. What if you're paving over an old existing road? An overlay?
Then you often need more prep work, things like crack filling or sealing to prevent water getting into the base, maybe surface leveling with a thin layer of mix to fill in ruts or low spots before the main overlay, and definitely patching any areas of severe distress.
Patching, like digging out bad spots.
Yes, it could be full-depth patching if the failure goes all the way down to the base or subgrade. That's a structural fix. Or it might just be surface patching if only the top asphalt layers are distressed.
Gotcha. Now, what about paving over old concrete roads? PCCP, Portland Cement Concrete Pavement. I've heard that's tricky because cracks from the concrete can come right up through the new asphalt. Reflection cracking, right?
Exactly. Okay, let's unpack this because reflection cracking is a major headache when overlaying concrete. Those joints and any existing cracks in the rigid concrete slab act like stress points. As the concrete expands and contracts with temperature or moves under traffic loads, those movements concentrate at the cracks and joints.
And they just transfer straight up into the new asphalt overlay.
Precisely. The new flexible asphalt just can't resist that concentrated movement from the rigid slab below, and a crack reflects through. It looks bad and it lets water in, shortening the overlay's life.
So how do engineers stop that? You can't just pave over it.
No, you need specific strategies. One is saw and seal. You actually saw joints in the new asphalt directly over the joints in the concrete below and then seal them. This controls where the cracking occurs.
Okay, manage the crack.
Another approach is to break the slab's continuity before overlaying. For plain, unreinforced concrete, they use a technique called crack and seat. They use equipment to induce fine cracks in the concrete, breaking it into smaller, stable pieces, maybe 3 to 4 feet across, and then use a heavy roller to seat those pieces firmly into the base.
So it breaks up the big slab movement?
Exactly. For concrete that has steel reinforcing bars, they need a more aggressive approach called break and seat. This requires heavier equipment to actually rupture the bond between the concrete and the steel, ensuring the pieces can move independently.
And is there an even more extreme method?
Yes, the most robust solution is rubblization. Specialized machines, like a resonant pavement breaker, RPB, or a multi-head breaker, MHB, basically shatter the old concrete slab in place into small, aggregate-sized pieces.
Wow. Just pulverize it.
Essentially, yes. It effectively turns the old cracked concrete road into a high-quality, well-compacted aggregate base layer. There are no slabs left to reflect cracks, so you get much better performance from the asphalt overlay. It's basically recycling the old road right there.
That's incredible. Okay, so surface prepped, reflection cracking dealt with. The paver finally gets to work. How does that machine lay down the mix so precisely?
The paver itself applies the mix, but the real magic happens at the back with a free-floating screed.
Free floating.
Yeah, the screed isn't rigidly fixed. It kind of floats on the asphalt mix itself. It applies the initial compaction and is the primary controller of matte thickness and smoothness.
How does it float at the right thickness? That sounds tricky.
It is. It relies on a balance of 5 interacting factors. You've got the screed's own weight pushing down, the resistance or stability of the asphalt mixture pushing back up, the paver's constant forward motion, the amount of material piled up in front of the screed, the head of material, and crucially, the screed's angle of attack relative to the surface.
Angle of attack, like an airplane wing.
Sort of. When all those 5 forces are in balance, the screed will naturally float at a consistent matte thickness. If the operator wants to change thickness, they adjust that angle of attack slightly.
And how quickly does that change take effect? Is it instant?
No, it's gradual. Adjustments to the screed for thickness changes happen gradually as the paver moves forward. The rule of thumb is it takes about 4 to 5 times the length of the toe arms connecting the screed to the paver tractor for the full change to be realized.
So if the toe arms are, say, 10 feet long,
Then you're looking at 40 to 50 feet down the road before the matte thickness fully stabilizes at the new setting. This prevents creating sudden bumps or dips. It has to be a smooth transition.
smoothness is key. And they use technology to monitor things in real time too, right? Like temperature.
Absolutely. Modern pavers often have infrared temperature monitoring systems, usually scanners mounted on the back. These continuously measure the temperature across the entire width of the freshly laid mat.
And what are they looking for?
They're looking for thermal segregation, significant temperature differences within the mat, maybe cool spots caused by those clumps from the truck, or uneven delivery. Detecting these temperature differentials allows the crew to take immediate corrective action, maybe adjusting plant temperature or trucking operations, because temperature is so critical for achieving proper compaction.
Which brings us neatly to compaction. perhaps the most critical step for making that road last. The manual really hammers this home, saying the resultant in-place density is perhaps the most important factor affecting performance throughout its life.
It really can't be overstated. Getting the mix compacted to the right density locks in all the performance characteristics designed into its strength, stability, durability, resistance to water damage. Low density is a recipe for early failure.
So what makes a mix easy or hard to compact? The manual mentions compactability.
Right. Compactability is just the relative resistance a mix offers to compaction efforts. Some mixes are easier to densify than others.
And what affects that?
Several things. The mix properties themselves are huge. A hotter binder is less viscous, acting like a lubricant between the aggregate particles, making it easier to compact. Stiffer binders, like those used in hot climates, require higher temperatures to achieve that lubrication effect.
So temperature is critical again?
Always. Environmental conditions also play a big part. Paving on a cold, windy day drastically shortens the time you have to compact the mix before it cools too much and becomes impossible to densify further. And the lift thickness matters too.
Lift thickness, you mean how deep the layer is?
Exactly. For dense graded mixes, the general rule is the layer needs to be at least 3 to 4 times the nominal maximum aggregate size, in MAS, the largest common particle size. If the layer is too thin relative to the aggregate size, the particles can't reorient themselves properly under the roller, making it really difficult to achieve density. You can also get that collapse of VMA issue we talked about if it's too thin.
Okay, so lots of factors affecting how easy it is to compact. What about the machines doing the compacting? The rollers. It's not just one type, right?
Not at all. You typically have a train of rollers working together. The main types are static steel-wheeled rollers, which rely purely on their weight for compaction. They often do the initial breakdown rolling or the final finish rolling.
Just heavy drums.
Yep. Then you have pneumatic tire rollers, often called rubber tire rollers. These have multiple smooth rubber tires, and their compactive effort can be adjusted by adding ballast weight or changing the tire pressure. They provide a kneading action that's good for sealing the surface, often used in the intermediate rolling phase.
Kneading. Interesting. And the third type?
The most common type for achieving density efficiently is the vibratory roller. These have steel drums, like the static ones, but they also have rotating eccentric weights inside the drums. These weights create vibrations, rapid impact forces that help densify the mix much faster than static weight alone.
So they shake the mix into place.
That's a good way to think about it. And vibratory rollers can operate in different modes. Static, vibrators off, vibrating just the leading drum, or vibrating both drums. The mode, frequency, and amplitude of vibration are chosen based on the mix type, the lift thickness, and the stage of compaction.
Lots of variables to control there. And the manual had a really important point about roller speed versus production rate.
Yes, and this is critical and often misunderstood on job sites. The manual states, increasing roller speed will not compensate for increased production rates. It simply reduces the compaction energy. You can't just drive the roller faster to keep up if the paver speeds up.
Why not? Seems intuitive. Go faster, cover more ground.
Because compaction depends on the amount of time the roller drum or tires are actually applying force to a specific point on the pavement. If you increase speed, you decrease that dwell time, reducing the energy imparted. You just don't achieve density.
So what's the right approach if production increases?
Increasing the number of rollers is the correct approach. You need more machines to provide the necessary compactive effort within the available time window before the mat cools. Roller travel speed is usually limited to a slow 3 to 5 miles per hour. That's about 5.8 kilometers per hour to be effective.
Okay, more rollers, not faster rollers. How do they figure out the exact pattern and number of passes needed?
That's typically done using a test strip at the very beginning of the paving project. They lay a short section of pavement and experiment with different combinations of rollers, patterns, and number of passes, taking density measurements along the way.
Like a calibration section.
Exactly. The goal is to determine the optimal number of passes and the rolling pattern for each roller in the roller train needed to consistently achieve the target density for that specific mix, on that specific day, under those specific conditions. Once established, that pattern is followed for the rest of the project, assuming conditions don't change drastically.
And are there specific patterns they follow, like where to start rolling?
Yes, proper roller patterns are important for uniformity. For instance, when compacting a lane, they typically start rolling near the edge and progress towards the center, overlapping each pass. On a sloped or super elevated curve, they always start on the low side of the mat and progress toward the high side.
Why low to high?
to prevent the mix from shoving or migrating downhill under the roller. Rolling uphill pushes against gravity and keeps the mix in place better.
Smart. And the manual mentions joints being a problem area.
Longitudinal joints, the seam between two adjacent paving lanes, are notoriously difficult. It's very common to have lower than optimum density along longitudinal construction joints.
Why is that?
Because one edge is unconfined when you pave the first lane, making it harder to compact right to the edge. And then matching density on the second lane against that cooled edge is tricky. This lower density makes joints prone to cracking and water infiltration, so they require extra attention during both paving and compaction. Special techniques are often used.
Okay, so after all that meticulous work design, production, placement, compaction, how do they finally ensure everything meets the standards? How has quality control itself evolved?
The whole approach to specifications has changed quite a bit over the years. It started way back with method specifications.
Method specs, like telling the contractor exactly how to do everything.
Pretty much. Defining the equipment, the procedures, the number of roller passes. Very prescriptive. The assumption was if you followed the method, you'd get a good result.
But that doesn't always work.
Not necessarily. And it didn't incentivize innovation.
So then came end result specifications. These focused more on testing the final product, checking density, smoothness, etc. after the work was done. The contractor had more freedom in how they achieved the result.
Better, but maybe too late if things go wrong.
Right, which led to the current state-of-the-art, quality assurance QA specifications. This is a much more comprehensive approach.
So, QA specs usually involve statistical sampling and testing throughout the process. Crucially, they often split responsibilities. Quality control, or QC, testing is done by the contractor to monitor and control their process. Acceptance testing is done by the agency, like the DOT, to determine if the final product meets the contract requirements. And often there's a third layer, independent assurance, or IA, where a separate third party verifies that both the contractors and agency's testing equipment and procedures are correct.
Wow, that sounds potentially complicated. Lots of parties testing.
It can be, which is why the pre-paving meeting is absolutely vital. It's not just paperwork.
What's the real goal of that meeting?
Two key things. First, to formally verify that the proposed job mix formula, JMF, will produce materials meeting the project specifications. But second, and critically, it's to ensure that contractor and agency technicians get acceptably consistent results on a split sample.
A split sample. They test the same bucket of mix.
Exactly. They take a sample of mix, split it, and have both the contractor's lab and the agency's lab run the same tests, like binder content, gradation, maybe VM. The goal is to identify and resolve any issues related to lab comparisons of testing and calibration before paving starts.
Ah, so you iron out differences in test results beforehand.
Yes. If you don't do that, you risk contention throughout the project, with labs getting different numbers and arguing over who is right. Resolving those differences up front saves enormous headaches later.
Makes perfect sense. Now, how do they actually get those samples during and after construction?
There are various sampling points. Samples can be taken right at the plant, from the hauling trucks at the plant or the job site, sometimes from the windrow if using bottom gums. But the most common method for checking the quality of the completed pavement is by cutting cores.
Cutting cores. Drilling out cylinders of the pavement.
Yep, using specialized wet-cut diamond drill rigs. They extract cylindrical samples right through the new asphalt layers. These cores are then carefully handled and taken to the lab for testing density, GME, thickness, and sometimes other properties.
And for the aggregates back at the plant or during mix checks?
They'll do sieve analyses. Sometimes a dry sieve analysis is used for quicker QC checks, just shaking the aggregate through the sieves. But for more precise acceptance testing, a washed sieve analysis is usually required. That involves washing the sample first to remove all the very fine dust particles that cling to the larger aggregates, giving a more accurate picture of the true gradation.
Okay, so for the final checks on the road itself, what does placement QC focus on?
Placement quality control focuses on temperature, compaction, thickness, and smoothness. Temperature is checked constantly, thickness is checked, often using the cores. And compaction, or density, is paramount.
How is compaction specified? Is it just a minimum density?
It's usually expressed as a percentage of a target density. The Asphalt Institute recommends the use of the theoretical maximum density, TMD, which is that GMM value we talked about, as the basis for calculation. So a typical specification might require the in-place density to be, say, 92 to 96% of the TMD. Each core's density, GMB is compared to the mix's GM to calculate the percent compaction.
92 to 96%. That range seems important. You don't want 100%.
No, you absolutely need some air voids left in the mix, usually between 4 and 8% for dense graded mixes. That provides space for a tiny bit of future compaction under traffic and space for the binder to expand slightly in hot weather without bleeding to the surface. Going much above 96 and 97% can lead to instability.
Got it. And that leaves the final factor, smoothness, which, let's be honest, is probably what most drivers notice first.
Absolutely. The manual says pavement ride quality or smoothness is the leading factor in the traveling public's perception of road quality. If it rides smooth, people think it's a good road.
But is it just about perception? Does smoothness actually matter for the road itself?
It does, significantly. Smoother pavements actually improve pavement durability, which extends the life of the pavement,
How so?
because bumps and roughness cause higher dynamic impact loads from vehicles. Hitting a bump puts extra stress on the pavement structure and on the vehicle itself. A smooth road experiences lower, more evenly distributed stresses, so it lasts longer.
That makes sense. And agencies actually incentivize smoothness.
Yes, many agencies offer significant incentives to contractors for building smoother pavements. And likewise, penalties if the ride quality doesn't meet the standard. It's a major focus.
How do they measure it objectively?
The standard method now uses inertial profilers. These are vehicles equipped with lasers and accelerometers that drive along the pavement and measure its longitudinal profile very accurately.
And that generates a number.
Yes, the data is used to calculate the International Roughness Index, or IRI. It's expressed in units like inches per mile or meters per kilometer. Lower IRI means a smoother road. The IRI value is often a key acceptance criterion, sometimes even triggering those bonuses or penalties. It's the ultimate measure of how well that whole complex process came together.
Well, we've certainly covered a lot of ground today. Pun definitely intended.
Yeah.
From the surprisingly complex behavior of that asphalt binder, acting like a liquid or a solid, to the meticulous synchronization of those giant machines, the plants, the pavers, the rollers, it's really clear that building a high-quality, durable asphalt road is, well, it's an invisible engineering marvel hiding right there beneath our daily commutes.
It truly is. It's a testament to applied science, material science, and some really meticulous planning and execution. Every smooth mile you drive is a direct result of countless precise decisions, constant testing, and flawless teamwork, all designed to make sure that road can handle traffic and weather for years, hopefully decades.
So the next time you find yourself cruising down a really smooth stretch of highway, maybe just take a second to consider that incredible symphony of materials, machinery, testing, and sheer planning that went into creating that seemingly simple black surface. Really makes you wonder, doesn't it? What other everyday structures that we take for granted hide such complex, interwoven processes just beneath the surface?